that.
Yes. Now, here is the full TTS-ready transcript.
Today we're going to take a deep dive into a problem that's quietly fueled our entire digital world. This just insatiable demand for faster data. Think about cloud computing, AI, every single byte flowing across the internet. It all relies on incredibly fast interconnects. And for decades, really, one fundamental technology, NRZ signaling, was the workhorse. But it finally hit a physical, undeniable wall. And this wasn't just some minor hurdle. It really demanded a complete paradigm shift. So we're going to explore that wall and the revolutionary technology that broke through it, PAM4. That's four-level pulse amplitude modulation. The true genius here, it isn't just about packing more data. It's really about this kind of revolutionary engineering pivot. It's the story of realizing, we couldn't just rely on perfect physical channels anymore, and instead intentionally moving the burden of signal fidelity, moving it from fragile wires onto, robust, intelligent silicon. This wasn't just an incremental step. It was a really strategic trade-off. It fundamentally redefined system design. That's exactly right. I mean, the problem was effectively moved, like you said, from the physical world of wires into the digital realm of silicon. And we'll unpack what that truly meant for system design, the surprising trade-offs that emerged, and how engineers really wrestled this complex beast into submission to power the speeds we all rely on today.
Yeah, fascinating stuff. And all of this insight, it comes directly from our comprehensive source material today, a document titled Module 2, PAM4 Physical Layer Deep Dive. So let's unpack this. Okay, so to really appreciate why PAM4 was so necessary, we first need to understand NRZ, non-return to zero signaling, sometimes called PM2, right?
Right, PM2. And its beauty really was its simplicity. You had two voltage levels representing a 0 or a 1 foot, and each symbol transmitted exactly 1 bit. So crucially with NRZ, your bit rate directly equaled your baud rate, your symbols per second. Simple, elegant, effective.
Until physics got in the way.
Precisely.
Yeah.
NRZ ran headfirst into what we call the bandwidth wall. You see, any electrical channel could be a copper trace on a circuit board, a backplane, a cable. It inherently acts as a low-pass filter, which just means it aggressively attenuates, cuts down the higher frequencies. So for NRZ, the critical frequency, that became its undoing. As data rates pushed towards, say, 56 gigabits per second, NRZ's required Nyquist frequency would hit an unmanageable 28 gigahertz.
Wow. And the numbers from our source material, they really paint a picture here. Like in IEEE 802.3 compliant backplane, for example, it might show manageable insertion loss, maybe around 33, 34 DMS at 14 gigahertz, manageable-ish. But at 20 gigahertz, that loss just skyrockets. It goes up to a prohibitive 62 dBit. I mean, that extreme attenuation, it essentially just annihilated the signal, created severe intersymbol interference, or ISI. So the signal's eye diagram at the receiver, that visual fingerprint engineers use to gauge signal quality, it'll be completely closed.
Yep, totally closed.
Like trying to read a flickering light in a pitch black room.
Yeah.
You literally couldn't tell a 0 from a 1, the ghost of the previous bit just blurring the current one.
Exactly. And this wasn't just a challenge. It was basically a dead end for NRZ at those speeds. To overcome that catastrophic level of loss purely with analog means, with equalizers, well, they would have needed equalizers of such immense complexity and power consumption, it would have been utterly impractical, just not feasible for commercial deployment.
So NRZ hit its ceiling.
It did. It was the workhorse for standards like PCIe 5.0 at 32 gigatransfers per second and 100G Ethernet, which used 4 25 gigabit per second NRZ lanes, but it simply could not scale to the next generation of per lane speeds. No way.
Okay, so NRZ hits this brick wall. Engineers can't just keep pushing harder. They need a fundamental rethink, a paradigm shift. And that's where PM4 steps in, not just as an improvement, but as this really clever end run around the physics. It breaks that direct link between how fast you send data and how wide your channel needs to be.
That's the core idea.
Instead of just 2 voltage levels, it uses 4 distinct amplitude levels. So each symbol can encode 2 bits of information, 0, 0, 0, 1, 10, or 11, instead of just 1.
And this is the fundamental innovation. For any given bit rate, PM4 requires only half the symbol rate or baud rate compared to NRZ. And that directly translates to having the required channel bandwidth, half,
which is huge.
It's huge. So revisit that 56 gigabit per second example. NRZ would need to operate at 56 gigabaud, right? With that 28 gigahertz Nyquist frequency, PAM4 achieves the same 56 gigabit per second throughput at a much lower 28 gigabaud. So its Nyquist frequency is only 14 gigahertz. It effectively sidesteps the most severe region of the channel's insertion loss curve.
Ah, okay. So it faces that more manageable 33 dB loss, not the crippling 62 dB.
Exactly. That's the trick.
And the practical implications of this clever trick were, well, massive, weren't they? It let the industry keep using existing copper interconnect infrastructure, PCB laminates, connectors, cables, even at much higher data rates.
Yeah, it bought time.
It bought precious time, delaying a far more expensive and frankly disruptive transition to entirely new, lower loss materials and technologies.
Absolutely. And we see PAM4's adoption just across the board now in modern high-speed standards. For instance, 400G Ethernet uses configurations like 8 lanes of 50 gigabit per second PAM4 or 4 lanes of 100 gigabit per second PAM4. And PCIe 6.0, that achieves its whopping 64 gigatransfers per second data rate by using PAM4. It doubles the throughput of PCIe 5.0's 32 GT's NRZ signal.
While keeping the same fundamental Nyquist frequency.
Right, keeping that same 16 gigahertz Nyquist frequency. It really was a pragmatic engineering decision, trading NRZ's simplicity for PAM4's bandwidth efficiency.
Okay, it sounds like PAM4 is the undisputed champion then. But are there, I don't know, any scenarios, maybe like very short distances or specific niche applications where NRZ still holds a surprising advantage? Because it seems like such a radical shift must come with, well, some trade-offs.
That's a great question. And yes, there are trade-offs. While PAM4 solved the bandwidth problem, it definitely wasn't a magic bullet. The trade-off for that spectral efficiency is a noticeable degradation in signal integrity. We fundamentally shifted from trying to transmit a clean, near-perfect analog signal to one that is inherently noisy and error-prone. And we did this with the explicit expectation that powerful digital processing at the receiver would, well, clean it up.
All right.
So for very short, pristine channels where bandwidth really isn't an issue, NRZ's simplicity and maybe its lower power consumption for a given error rate can still be appealing. But honestly, those use cases are becoming increasingly rare at the cutting edge.
Okay, so let's talk about that. What does this mean for the PAM4 signal itself? If it's inherently noisy, what does it actually look like?
Well, the eye diagram, that visual representation, it tells the story. An NRZ signal has that one single large eye, easy to see. But PAM4, with its 4 levels, it produces 3 smaller vertically stacked eye diagrams.
3 eyes instead of 1.
3 eyes. And this is crucial and often underappreciated. These 3 eyes are not identical. There's an inherent asymmetry. Because transitions between adjacent levels, like say 0 to 1, they have a different slew rate, a different speed than transitions that cross multiple levels, like 0 to 3.
Oh, okay.
This creates 12 distinct transition types, each with its own timing profile, and that leads to non-uniform eye widths. This complexity means, simple visual analysis just isn't enough anymore. You need sophisticated algorithmic approaches like NIST's k-means clustering to really characterize the signal properly.
So not only are the eyes smaller, but they're not even uniform. That does sound like an engineer's nightmare. But you mentioned the most significant penalty, the unavoidable one, is its signal-to-noise ratio degradation, the SNR. Why is that?
Absolutely. It's fundamental because you're packing 4 voltage levels into the same total signal swing that NRZ used for just 2. The vertical distance, the height, between any 2 adjacent levels in a PAM4 signal is only 1/3 the height of an NRZ eye.
Only a third. Wow.
Yeah. And to put a number on it, this directly translates to a fundamental link budget loss of approximately minus 9.54 dBs. That's calculated as 20 times log base 10 of 1/3.
Minus 9.5 dB.
It's not just a number. It's the fundamental reason why PAM4 demands this completely new mindset for handling noise and errors. It's basically a recognition that perfect analog transmission, well, it's kind of a pipe dream now at these speeds, and we have to rely on digital wizardry to clean up the mess.
So the signal is just much more sensitive.
Acutely sensitive to all forms of noise and channel impairments. Its tolerance to noise is reduced by a full 67%. So things like crosstalk, reflections, power supply noise, they all have a much, much greater impact, making pristine signal integrity a non-negotiable requirement for the entire system design.
That degradation sounds, well, catastrophic. How is it even possible to recover a usable signal from something so inherently noisy? Is there some digital magic happening behind the scenes?
That's precisely where forward error correction, or FEC, becomes absolutely critical. It's a mandate. You see, PAM4 links inherently operate with a much higher raw BER, the pre-FEC bit error rate,
Right.
typically ranging from, say, 10 to the minus 6 down to 10 to the minus 4.
Which is way higher than NRZ.
Oh, way higher. NRZ was often less than 10 to the minus 12. So it's simply not feasible to design the channel and receiver to hit those classic BER targets like 10 to the minus 12 or 10 to the minus 15 purely through analog means with PAM4. So FEC works by adding redundant information at the transmitter, extra bits. The receiver then uses this redundancy to detect and, crucially, correct errors digitally. That brings the post-FEC BER down to usable levels, like that 10 to the minus 15 target.
Okay, so it cleans it up after the fact.
Exactly. And FEC is now mandatory in key standards. IE 802.3 for 200G, 400G Ethernet, PCIe 6.0, they all require it. Now, yes, it adds its own overhead, there's latency, there's power consumption. But this is a well-defined, manageable cost within the silicon, and frankly, it's a far more efficient solution than attempting the impossible, trying to build a perfect, error-free analog channel at these speeds.
Okay, that makes sense. So given this inherently noisy signal and the total reliance on FEC, equalization then becomes, well, not just an enhancement anymore, right? It's an absolute necessity. The signal, when it arrives, literally has completely closed eyes because of ISI. It's just unreadable without help.
Precisely. The core of a high-speed SerDes, that's the serializer-deserializer, is its equalization circuitry. And the engineering strategy is to distribute this effort intelligently between the transmitter, the TX, and the receiver, the RX. We primarily use three key techniques. There's feed-forward equalization, FFE, in the transmitter. Then there's continuous time linear equalization, CTLE, in the receiver's analog front end. And finally, decision feedback equalization, DFE, which is deep within the receiver's digital processing.
Okay, 3 stages: FFE, CTLE, DFE.
Right. FFE is a digital filter in the transmitter. It basically predistorts the signal to proactively counteract predictable channel loss. It's like sending a pre-equalized signal. But its main drawback is that it kind of indiscriminately amplifies all high-frequency content. That includes undesirable noise and crosstalk, which is particularly bad for the already low SNR PAM4 signal.
Right, you don't want to boost the noise.
No. Then CTLE, that's an analog high-pass filter in the receiver. It boosts the attenuated high-frequency components, helps sharpen up the signal edges. But like FFE, it's linear, so it also amplifies noise along with the signal.
Okay, so FFE and CTLE help, but they also amplify noise. What about DFE?
Ah, DFE. This is where the real magic happens, arguably. It's the most powerful and critical technique because it removes post-cursor ISI that's interference from previously transmitted symbols, and it does it without amplifying high-frequency noise.
How does it do that?
It's a non-linear feedback-based system. So after the receiver slices the signal and decides what symbol it is, that digital decision is fed back into the analog path, and it's used to subtract the ISI that decided symbol would cause from the next incoming symbol before it gets sliced.
Oh, that sounds incredibly clever, almost like it's learning from its own decisions as it goes.
It is, in a way.
But if it's so powerful, why is DFE so much more complex for PAM4 than it ever was for NRZ? What's the challenge there?
That's a really crucial distinction. An NRZ receiver, it has a single slicer, right? With one decision threshold right in the middle. A PAM4 receiver, however, needs 3 slicers to make decisions for its 3 eyes simultaneously.
3 slicers instead of 1.
3. And the DFE feedback loop has to handle these multi-level decisions, which just necessitates more complex hardware, more gates, and it consumes more power. Plus, there's a greater concern for something called error propagation. If the slicer makes one wrong decision,
Oh, I see.
that incorrect feedback can actually cause subsequent errors. It can snowball.
Right.
So innovative architectures like pipeline DFEs are really crucial for mitigating that risk.
Okay. So you have these different stages, FFE, CTLE, DFE, all working together. How do you optimize them? Do you just tune each one individually?
No, that's the thing. This brings us to the concept of joint optimization for global performance. It's really critical to understand that optimizing each stage, FFE, CTLE, DFE in isolation, that leads to suboptimal results, often significantly suboptimal. These equalizers, they're a deeply interdependent system. They all affect each other.
Okay.
So the goal is to find a single set of coefficients, a single tuning, where the linear equalizers, the FFE and CTLE, they create maybe just a partially open eye, but without boosting the noise too much. And then the DFE comes in and fine-tunes it, using its noise-free advantage to really open up those 3 eyes.
That sounds like a really complex balancing act.
It is.
Yeah.
It's a complex, multidimensional optimization problem. But the good news is it's now highly automated by modern electronic design automation, or EDA, tools and algorithms. They analyze the channel's response, how it affects the signal, and then calculate the optimal settings for all the equalizers jointly. It's really a testament to the ingenuity required to make PAM4 actually work reliably.
Okay, so we've covered the signal itself, the noise, the equalization. But beyond the signal, PAM4's reduced eye dimensions and this complex nature, it must place unprecedented demands on the timing subsystems too, right? Our tolerance for timing errors, for jitter, must be drastically reduced. What does that mean for the clock and data recovery circuits?
Indeed. The demands are intense. The fundamental function of the clock and data recovery, the CDR circuit, is to extract a stable clock from the incoming data stream and then sample that data at the optimal point in time. With PAM4, the CDR's phase detector, the part that locks onto the signal timing, it is a lock onto a signal with 3 small, noisy eyes.
Yeah.
And those 12 different types of transitions we talked about, each with a unique slew rate, a unique edge speed. This causes inherent data-dependent jitter that the CDRs just have to contend with. It's baked into the signal. So modern CDRs often use advanced architectures, like phase interpolator architectures with specialized baud rate phase detectors, to handle this complexity effectively.
Okay, so more advanced CDRs are needed.
Definitely. And for state-of-the-art retimers, say, operating at 112 gigabits per second, like those used for PCIe 6.0, we actually see a really sophisticated approach. It's called a dual-loop CDR plus PLL approach.
Dual loop, how does that work?
Well, the main CDR loop recovers a clock directly from the noisy PAM4 data. It tracks the data closely, but that recovered clock is inherently a bit noisy itself, right? It contains jitter from the data.
Okay.
This dirty clock is then fed into a second independent phase-locked loop, a PLL, but one with a very narrow loop bandwidth. This narrow band PLL acts as a highly effective jitter cleaning filter. It essentially rejects the high-frequency jitter present on the recovered clock and produces an ultra-stable, very low jitter clock for the rest of the receiver circuitry.
Ah, that's clever. So it separates the job of tracking the data from the job of cleaning the clock.
Exactly. It separates data tracking from jitter filtering, which allows you to achieve both low-latency data recovery and extremely low output jitter. A really neat solution.
So if I'm hearing you correctly then, with PAM4, the whole way we understand and specify jitter has fundamentally changed. What does transition-dependent jitter even mean when you're talking about so many different signal types?
It means jitter is no longer just a single monolithic value like we might have thought about with NRZ. It's really a statistical distribution, and it depends heavily on the specific data pattern being transmitted.
Okay.
So think about it like this. Consider a 0 to 1 transition in PAM4. That has a relatively slow slew rate, right? A shallow slope. Now compare that to a 0 to 3 transition, which is a big jump, a very fast slew rate across the full voltage swing, a steep slope.
Got it. Slow versus fast edges.
Right. Now, any vertical noise on the signal, maybe from power supply fluctuations or crosstalk, it's going to perturb the signal's amplitude, move it up or down slightly. This amplitude perturbation translates directly into timing jitter at the receiver's slicer threshold. But crucially, that same amount of vertical noise, say 10 millivolts, will cause a much larger amount of timing jitter on that slow 0 to 1 transition than it will on the fast 0 to 3 transition, because the slope is shallower.
Ah, okay. The same noise pushes the timing further on a slower edge.
Exactly. So the implications for system design are significant. Jitter isn't one number. It depends on the pattern.
Wow. Okay, how do standards deal with this?
Well, PCIe 6.0 provides a really clear case study for this new jitter paradigm. First, the measurement methodology itself is different. Instead of trying to extrapolate total jitter down to very low BERs, like 10 to the minus 12, which was common for NRZ, direct measurement at a higher BER, like 10 to the minus 6, is now possible and actually required. That's a major shift in how we characterize links.
Direct measurement at higher BER.
Second, they use a specific jitter pattern. It's a 52-unit interval repeating sequence, and the sequence is meticulously designed to exercise all 12 of the possible PAM4 transitions, making sure the test is comprehensive.
Right, got to test all the edge types.
Exactly. And third, the key metric itself is now called uncorrelated total jitter, or UTJ. And its calculation is far more granular. It requires measuring the random jitter and the uncorrelated deterministic jitter components separately for each of the 48 transitional edges within that specific 52 UI pattern.
Each edge gets measured.
Wow.
Yeah, it's a complex, multifaceted approach. But it acknowledges the reality that the total link jitter is actually a composite of many different jitter distributions, all depending on the data pattern. So it sounds like keeping this really complex, pattern-dependent jitter within a tight tolerance is absolutely critical for reliable PAM4 links. Designing these systems requires a whole new level of precision and insight. Okay, as we wrap up this deep dive, it's abundantly clear the transition to PAM4 wasn't just an upgrade, it was truly a paradigm shift, forced really by that bandwidth wall of NRZ. And it represents this core engineering trade-off, intentionally sacrificing, that analog signal purity for digital processing complexity.
That's a perfect summary. And if we connect this to the bigger picture, the burden of performance, it has decisively shifted. It's moved from the physical medium, the copper, to the silicon, to the chip itself. We've seen the critical role of sophisticated co-optimized equalization, that FFE, CTLE, and DFE all working together in concert. We also looked at the intense clocking demands and this much more nuanced understanding of pattern-dependent jitter that's required just to make these systems function reliably at all.
And it's this strategic pivot, this move to digital processing, that has made PAM4 the cornerstone technology for today's highest speed interconnects, powering everything from 200G and 400G Ethernet all the way to 64GT's PCIe.
Which, it raises an important question as we look ahead. As the industry is already pushing towards 224 gigabits per second per lane and even beyond, how will these principles that were established during this PAM4 transition, things like holistic system design, the absolute primacy of sophisticated digital signal processing, and this acceptance of managed error rates corrected by FEC, how will all that continue to shape the future of high-speed signaling?